I'm setting up a series of staged energy problems for you to rip through lots of different practices, but you don't learn anything new. You're just becoming mechanically good. If you don't understand the root concept, these drill-style problems will make you proficient at passing tests, but you won't understand in the end what you're doing. It's why I've been saving them to the end. And they are going to span all the units so far. But I'm going to show a slightly different technique for executing problems when you're having difficulty. There are two ways of setting up problems that you need to be good at: itemizing the variables on the left and drawing the free body diagram on the right. Now, I've been providing you a lot of free body diagrams, but you do need to start drawing them because you will be asked to do so next year. So pay attention to how I do these free body diagrams. Now I want to show you the difference between a list-based problem and as a word problem. Typically you might be asked a question like this: a green medicine ball of 50 kilograms mass travels 100 meters in 10 seconds while continuously accelerating from a starting speed of 0. Force operates in the ball at 0 degrees from the horizontal. The ball is rolling on the surface of friction coefficient of 0.03. Compute the ball's acceleration, final speed, force, friction force, gravity, net force, implied force in the ball. Also, what is the total work done compared to the kinetic energy? These word problems can be brutal, particularly if you're an ESL student. You're being tested on your grammar more than on your physics. So that's where I like to itemize them like you see on the left. Now we started with D, VI, VF, A, and T in the course. Then we added mass, then eventually angle and friction. And now we've added a bunch of force components and energy. So the list grows. And most of the time you would not need this entire list. You would only be using a fraction of it. But if we want to hit you with problems that span everything, the list does get a bit long. And like I said, you learn nothing by doing these problems other than getting good at doing problems. So I save them for later to put you through all the possible exercises you could experience from other teachers at other schools. Creating a good physics problem is kind of like making a mystery novel. The teacher works backwards. So I start with my own values and I start calculating the bottom here. So what's the first thing I can do to use these values to start filling in the missing ones? Well, the first one is pretty easy. Given that we have both speeds and time, I can do the V average T. I get my 150 meters. I can also do acceleration from the given data, and I get 3 meters per second squared. And since there is no angle in this situation, we're pulling dead straight, this is going to mean that f of x and f applied are going to be the same thing. There's going to be no difference between the applied force and f of x, so thankfully no trig. And we can also compute the force of gravity given the initial values. But now we have to start using calculated values in a moment. Kinetic energy is also available to us right off the bat. So now we move forward. I write in all my calculated values and I'll see what can we solve for now that we have more of these values filled in. Well, the net force is now available as 3,600 newtons because we have acceleration. And the force of friction is doable because we have mu mg, no problem. Okay? Now, I could have solved for the force of friction beforehand, but it crowds the plate in a way. The applied force is going to be the total force minus the force of friction. And the x force, remember, is going to be the same. It's being without an angle. We can even state by conservation of energy that the work is the kinetic energy and it's 540 kilojoules. So look at that. I've almost completely filled everything in 2 steps. So what does a teacher do? Then I go, I know it'll work. So I fill in all my values that I gave you, and I erased the starting ones, and I said, now you can try that one. So this is how a lot of teachers make the problem. We have to make sure the values work and then delete them. So now, knowing how I got here, let's solve it together and see what you get. So I'm going to lay out now a different set. These are simply the ones we solved for, and we're going to see, could we possibly go backward from all these values to the original kinematics conditions that set us up. And this is like an absolutely absurd problem. It has no bearing on reality other than sometimes you can hunt out real-world values by careful collection of other data. But it's not a place I would ever start a course, and I would only do it to give you a mathematical challenge, but it does not increase your understanding of the universe. Given that we have the work in kinetic energy, we can work backwards. If work is force times distance, then distance is work over force. So this thing is going to travel 150 meters. Given the net force, we already know that's m times a, so acceleration is F over m equals 3 meters per second squared. So it is working backwards. We're getting the values from the last slide. And given the force of gravity of 12,000 newtons, we work backwards and we get our 1,200 kilograms. And we can keep going like that, finding out the values that we were originally started with. Now, at this point, I can't calculate anything else. Like, the idea is, what can I calculate at the start? And the only things I can calculate at the start are these 4 things. Now we see if we can target the remaining ones. Can we solve for them now? And we have a problem. We have a big problem here. If we assume that speed initial is not 0, we have these 5 problems and we have too many unknowns in it. Because I didn't give you VI equals 0, it becomes a terribly difficult problem to solve. But if you can assume VI is 0, all these equations simplify and it's easy to solve for the remaining data. So which one would I give you? Well, I would never give you the one without VI to begin with, because that's really too hard. It would be strictly a challenge. So if I let you assume initial speed is 0, then taking EK and reversing it out is very easy to solve for that. And then it's just a child's play to go ahead and get the time. Now, would I expect you to draw this in your notes? Oh, heck no. But this shows you the logical steps as you move forward on here. And if you really want a challenge, you could see if you could figure out a solution if VI does not start at 0. Let's try one together. You can pause the video at this point, capture these values, and see if you can solve for the missing values. I will start the solution in just a moment. Alrighty, let's begin the solution. What's the first thing we can possibly calculate here? Well, we have a problem. We're definitely going to have a VF and we've got an angle. So it's definitely going to require trig at some point. But it looks like, given 400 meters in 10 seconds, and we know it's accelerating because the problem should have stated so, even though it doesn't, we have a VI is equal to 0. So there's no way with a starting speed of 0 that you can cross 400 meters without an acceleration. If we take d equals VIT plus half AT squared, we're lucky. It just voomp vanishes and we can solve for the distance and the time and figure out what A is. So 800 divided by 100 seconds squared, we get 8 meters per second squared. Pretty good acceleration. We luck out, it's frictionless, so force of friction is automatically 0, and mg is also easy to calculate off the given values. So we've already picked up 3 values in a single step, and then we can calculate the next series of values. Once we know 8 meters per second squared, we can automatically calculate final speed. With acceleration, we can automatically account for net force, and we can work out the work done on the object. So that single solution for A promptly gives us 3 more solutions. Now, what do we have left? There's only a few values we don't have. Given that MA must come from F of X and force of friction, and knowing that the force of friction is 0, it turns out the force in the X direction is the same as the net force. They're the same because there is no friction. Taking the final speed and the mass, we can calculate the kinetic energy, and oh joy, it came out to be the same as force times distance, so it seems to indicate we're on the right track. What have we got left to go? Now we go to our trig. We know that the force in the X direction had to be 960 newtons. So now we're knowing this answer, we have to figure out the little Freddy problem with the pull on the angle. So trig comes into play, we do a basic calculation, and you'll get 1108 newtons to the right, upwards by 30 degrees. That's the solution laid out in this sort of linear strip fashion. A 3-person ATV that is persimmon in color with fuchsia stripes is driving through the Superstition Wilderness through rough sand with a frictional coefficient of 0.7. In a 10-second burst of acceleration, the ATV reaches 60 meters a second. Assuming it started from rest, compute the acceleration and force, friction, force, and blah, 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 blah. Just itemize it. There we go. What could we start with? Well, it looks to me like I have enough to compute the acceleration. And that acceleration is already that sweet, sweet thing that lets us carry on so many more calculations. And we also had enough to do the distance with the V average T. And enough to do the weight, the force of gravity. Oh my goodness, it's like a cornucopia. It's like Christmas in October. There are so many things. Oh, but another one. Look at all the things we could solve for at once. Well, that's just amazing. We've just about slaughtered this problem. There's only like sort of 1 or 2 things left here. There we go. We can get our net force now because we got that acceleration. But we still don't know what the applied or the X force is. So we have to move on a little bit more to solve for those. Now the X force is going to be simple. You need 4,800 newtons left over to cause the observed acceleration. The friction force is 5,600 newtons. Okay? And that means the force pulling in the X direction has to leave 4,800 left over after it successfully fought 5,600 newtons of friction. That gives us 10,400 newtons in the X direction. But now we can also solve for work if we want to. We could have done it earlier, but now it's really easy to solve for work as well. And it came out to 1.44 megajoules, exactly what we got for kinetic energy. So this is looking hopeful. Now we have to convert the X force to the hypotenuse of the triangle it would have come from, and we find 10,560 newtons. 10 degrees down from that, the X component of the force is only shrunk a little bit, which makes eminently good sense because it's only 10 degrees. And of course, that triangle is not proportional. So this one worked out pretty straightforward. Not a big deal. Here's another way of doing this, more conducive to doing it on pen and paper work without all the highlighters like I showed previously. Make a list of your variables on the left side of your page, and we'll start moving forward with the calculations as we go. there's a pretty obvious 5 that we can calculate from the get-go. Distance equals v average t, compute the acceleration with the giving numbers, and we can do 3 more. So we can literally do 5 out of the 7 in our first step, but we were unable to calculate F and F applied. The answers, you notice I wrote 56 kilonewtons and 80 kilonewtons. It's a lot more civilized. Rather than writing 56,000 to write 56 kilonewtons, and you read that as 56,000 newtons. The numbers are going to start getting really large because forces and energies are often extremely large or extremely small as we go into astronomy and atomic physics. Now we're down to 2 that we need to still solve for, but we can only do 1 at this step. We can find our total force, which is 2.2 times 10 to the 4th newtons. 4 zeros, if we borrow 1, it's 22 times 10 to the 3. So this number is 22,000. That makes it 22 kilonewtons. We have 1 thing left to solve for. The applied force is one of the 2 forces that add up to 22,000 newtons. So the applied force plus the friction force have to leave 22,000 left behind. So we have to add the friction onto the applied force, onto the force we need to get a larger applied force. The applied force has to be 78,000 newtons. So when 56,000 newtons come off as friction, we still have 22,000 newtons to accelerate. And you might find doing the equations sideways of the variables helps out a lot, particularly in typing. Don't become obsessed with the organization, but this might be another way of lining it all up so you can solve for the equations in rather quick order without getting lost on the page like some of you are doing.